The global refining industry processes 100 million barrels of crude oil every day. Without it, modern civilization stops. You have brought the oil out of the ground, drilled it, completed it, produced it, separated it, and shipped it across an ocean. You now have a tanker full of crude, but crude is useless. You cannot put it in a car. You cannot run a power plant on it, not efficiently, not cleanly, not at scale. Crude oil is a mixture, the lightest methane to the heaviest asphaltenes, all mixed together in a black, viscous soup that the earth cooked over 100 million years. To turn that soup into gasoline, diesel, jet fuel, and the petrochemical feedstocks that become plastics, pharmaceuticals, and fertilizer, you need a refinery. And a refinery is not a factory. It is a city of fire and chemistry. It operates at temperatures that would melt steel and pressures that would crush a submarine. It runs 24 hours a day, 7 days a week, 365 days a year, because you cannot simply turn off a refinery. Unit runs into tens of millions of dollars. Through wars, through pandemics, because the world cannot wait for its fuel. Science, the engineering, and the economics that turn a barrel of crude into the products that power modern civilization. Intervals, typically 30 to 50 trays. The vapor bubbles up through the liquid. Points rise higher. Heavier components condense and fall. At each tray, a partial separation occurs. Trays, the separation sharpens into distinct fractions. Top of column, below 40 degrees Celsius. Light ends, methane, ethane, propane, butane. Refinery fuel gas, some goes to the petrochemical plant. Upper section, 40 to 200 degrees Celsius. Naphtha, the precursor to gasoline. Straight-run naphtha goes to the catalytic reformer to boost its octane. Heavy naphtha may be blended directly or sent to the isomerization unit. Middle section, 200 to 300 degrees Celsius. This becomes Jet A1, the fuel that powers nearly every commercial aircraft in the sky. Gas oil. After hydrotreating, this becomes ultra-low sulfur diesel, the fuel that powers trucks, ships, trains, and heavy equipment globally. Bottom of column, above 350 degrees Celsius. Atmospheric residue, the heaviest fraction, too heavy to vaporize at atmospheric pressure. Atmospheric distillation unit, the CRUDE unit, is the mother of the refinery. Stops, the entire refinery stops, and it is, in principle, one of the oldest and simplest industrial processes in existence. Boil a liquid, separate the vapors by boiling point, and condense them into products. But the scale and precision at which a modern refinery does this is staggering. Remove salt, sediment, and trace metals that would corrode downstream equipment and poison catalysts. Then it passes through a series of heat exchangers, streams leaving the column, until it reaches the crude furnace. The furnace heats the oil to roughly 370 degrees Celsius. At that temperature, most of the hydrocarbons in the crude vaporize. The mixture of vapor and liquid enters the flash zone of the distillation column. It is driven by boiling point. Rise straight to the top where they are drawn off as refinery fuel gas. Condenses in the upper trays. Kerosene, the jet fuel fraction, in the middle. Diesel, the truck and ship fuel, lower down. And at the bottom, the atmospheric residue, the heaviest material, molecules so large and heavy that even at 370 degrees, they remain liquid. This is the simplest possible description of a intermediate product, not finished fuel, and the atmospheric residue, roughly 40 to 50% of a barrel of heavy crude, still contains enormous value if you can get at it. The atmospheric residue leaving the bottom of the crude unit is hot, heavy, and still contains enormous value. Pressure, you will not distill it. you will destroy it. The molecules will thermally crack, breaking apart randomly, producing gas, coke, and low-value products. To separate the heavy fraction cleanly, you must reduce the pressure. The vacuum distillation unit is the second mother column of the refinery. By lowering the pressure to near vacuum conditions, the boiling point of the heavy hydrocarbons drops dramatically. Degrees to boil at atmospheric pressure will vaporize at a manageable temperature under vacuum. The vacuum column produces three streams: light vacuum gas oil, which goes to the hydrocracker or the fluid catalytic cracker to become gasoline and diesel; heavy vacuum gas oil, which feeds the catalytic for lubricants; and vacuum residue, the very heaviest fraction, material that is almost solid at room temperature. The coker, where it is thermally cracked into lighter products and petroleum coke; the vis breaker, where it is mildly cracked to reduce its viscosity; or the fuel oil pool, where it is blended and sold as bunker fuel for ships, as asphalt for roads, or as fuel for power plants. The catalyst and oil mix in the riser. In roughly 2 to 3 seconds, the residence time, the heavy hydrocarbon molecules are cracked into lighter molecules. The catalyst surface provides the acid sites where carbon-carbon bonds break. The reaction produces gasoline-range molecules, light gases, and a byproduct, coke, pure carbon, which deposits on the catalyst surface, deactivating it. The cracked vapor, so now rich in gasoline-range molecules, rises to the main fractionator where it is separated into fuel gas, LPG, FCC gasoline, light cycle oil, and slurry oil. The FCC gasoline is the single largest source of gasoline in most refineries. The atmospheric and vacuum distillation columns separate crude by physical boiling point. But separation alone cannot meet the world's demand for gasoline and diesel. The crude unit produces far more heavy gas oil and residue than the market wants, and far less gasoline than the market demands. Conversion units bridge that gap. They break heavy, low-value molecules into light, high-value products. Catalytic cracker is the workhorse of conversion. It takes heavy gas oil from the vacuum unit, material that would otherwise become low-value fuel oil, and cracks it into gasoline, LPG, and light gases. The key to the FCC is the catalyst, a zeolite, an aluminosilicate mineral with a precisely engineered pore structure. The pores are roughly the size of the molecules being cracked. When a heavy hydrocarbon enters a zeolite pore, it is exposed to acid sites that break carbon-carbon bonds, producing lighter, more valuable molecules. The shape and size of the zeolite pores determine which molecules are cracked and which products are formed. Refiners select catalysts with different pore architectures depending on whether they want to maximize gasoline, maximize propylene for petrochemicals, or process heavier feedstocks. The hydrocracker is the refinery's premium conversion unit. It takes heavy vacuum gas oil, or in some configurations, atmospheric residue, and converts it into exceptionally clean, high-quality products. The diesel from a hydrocracker has a high cetane number. It ignites readily and burns cleanly, and requires minimal additional treatment. The kerosene fraction is nearly finished jet fuel, and because the process operates under hydrogen pressure, the products are inherently low in sulfur and other contaminants. Hydrocracking is more expensive than catalytic cracking, both in capital and in operating cost. The high-pressure hydrogen environment requires thick-walled reactors, specialized metallurgy, and a hydrogen production plant, typically a steam methane reformer that converts natural gas into hydrogen. But the product quality justifies the cost, particularly in refineries that process heavy, high-sulfur crudes and need to meet ultra-low sulfur fuel specifications. After roughly 16 to 24 hours, the drum is full of coke. The feed is switched to a parallel drum. The full drum is cooled, opened, and a high-pressure water jet, operating at roughly 350 bar, cuts the coke out. The coke falls out the bottom of the drum as a black granular solid. It is either sold as fuel, petroleum coke is burned in cement kilns and power plants, or, if it meets a higher purity specification, it is calcined and used to produce anodes for aluminum smelting and electrodes for electric arc furnaces. And then there is the coker, the refinery's last resort. When the crude is so heavy and the conversion unit so full that there is nowhere else for the residue to go, it goes to the coker. Delayed coking is a thermal cracking process. No catalyst, no hydrogen, just heat and time. The residue is heated to the point where the carbon-carbon bonds break, producing lighter products, gases, naphtha, gas oil, and leaving behind solid carbon, petroleum coke. Conversion technology in the refinery. And for the heaviest crudes, the Venezuelan, the Canadian oil sands, bitumen, the Mexican Maya, it is often the only option. The hydrogen sulfide is then stripped from the product stream and sent to the sulfur recovery unit, the Claus process. In the Claus unit, hydrogen sulfide is partially oxidized, then reacted over a catalyst bed to produce elemental sulfur, the bright yellow solid that piles up at refineries worldwide and is eventually shipped to manufacturers of sulfuric acid, fertilizer, and industrial chemicals. Conversion is only half the battle. The products leaving the crude unit, the FCC, and the hydrocracker still contain sulfur, nitrogen, and other contaminants that must be removed. Sulfur in gasoline reduces the effectiveness of catalytic converters. Sulfur in diesel produces particulate matter and acid rain. Regulatory limits: ultra-low sulfur diesel in the United States contains a maximum of 15 parts per million sulfur, down from 500 parts per million before 2006, have driven enormous investment in hydrotreating. Hydrotreating is the refinery's cleanup process. It operates on the same principle as hydrocracking, high-pressure hydrogen catalyst beds, but at milder conditions and with a different objective. The goal is not to crack molecules, but to strip removed as hydrogen sulfide. Nitrogen is removed as ammonia. Metals, nickel, vanadium, deposit on the catalyst surface and are eventually discarded with the spent catalyst. Is the refinery's environmental backstop. Without it, the hydrogen sulfide stripped from the product streams would be flared, producing sulfur dioxide, the primary cause of acid rain. A pollutant into a saleable product. Global sulfur production from refineries exceeds 60 million tons per year, most of which becomes sulfuric acid, the most widely produced industrial chemical on Earth. In the reformer, naphtha passes over a platinum-based catalyst at roughly 500 degrees Celsius and moderate pressure, converting straight-chain paraffins into branched isomers and aromatic rings. Significantly higher octane ratings. Rating of 90 to 105. It is the single most important octane boosting component in the gasoline pool. A valuable byproduct of reforming is hydrogen, significant quantities of it, which are recovered and used to feed the hydrotreaters and the hydrocracker. The reformer is thus both a product quality unit and a hydrogen source, a dual role that makes it essential in virtually every fuels refinery. The catalytic reformer serves a dual purpose that makes it essential. It transforms low-octane naphtha into high-octane reformate, the backbone of the gasoline pool. And in doing so, it produces hydrogen, large quantities of it, that the refinery uses to feed its hydrotreaters and hydrocrackers. The reformer is both a product quality unit and a hydrogen plant. Without it, the refinery would need to buy hydrogen or build a dedicated steam methane reformer at enormous capital cost. Finished gasoline, approximately 19.5 gallons, 46%. Diesel and heating oil, approximately 12.5 gallons, 30%. Jet fuel/kerosene, approximately 4 gallons, 9.5%. Heavy fuel oil, approximately 1.5 gallons, 3.5%. LPG, naphtha, petrochemical feedstocks, asphalt, lubricants, coke, sulfur, the remainder. But these numbers are not fixed. A refinery configured for maximum gasoline, a cracking refinery common in the United States, can push gasoline yield above 50%. A refinery configured for middle distillates, diesel, jet fuel, heating oil, will yield more diesel and less gasoline. The configuration depends on the crude slate, the refinery's hardware, and most importantly, the market. The final blend must meet up to a dozen specifications: octane number, vapor pressure, distillation curve, sulfur content, aromatics content, olefin content, benzene content, and more. The blender's job is to hit every specification at minimum cost. squeezing fractions of a cent per gallon out of the blend optimization, because fractions of a cent per gallon multiplied by the 100,000 barrels per day that a large refinery produces is millions of dollars per year. The final step in the refinery is blending, and it is perhaps the most commercially sensitive. Each finished product, gasoline, diesel, jet fuel, is not a single stream from a single unit. It is a carefully calculated mixture of components from across the refinery, blended to meet dozens of specifications while minimizing cost. A single barrel of crude refined and blended yields roughly 45 gallons of finished product, 3 gallons more than the input barrel, a phenomenon called processing gain, caused by the reduction in density as heavy molecules are cracked into lighter products. That 45 gallons becomes the fuel in your car, the jet fuel in the aircraft overhead, the diesel in the truck delivering your food, and the petrochemical feedstocks that become the plastics, pharmaceuticals, and fertilizers that underpin modern life. The spread fluctuates. It widens when product demand is strong or when refinery capacity is constrained. After a hurricane knocks out Gulf Coast refineries, for instance. It narrows when crude prices rise faster than product prices, typically during supply disruptions or geopolitical crises that spike crude without directly affecting refining capacity. The economics of refining are brutal, cyclical, and occasionally spectacular. The key metric is the crack spread, the difference between the price of crude oil and the price of the refined products. The 3-2-1 crack spread, 3 barrels of crude into 2 barrels of gasoline and 1 of diesel, is the industry benchmark. When the spread is wide, refineries print money. When it narrows, when crude prices spike and product prices cannot keep up, refineries lose money on every barrel they process. The Nelson Complexity Index measures a refinery's ability to create value from a barrel of crude. A simple refinery, just a crude unit and a reformer, might have an index of 2 to 3. It can process light, sweet crude and produce gasoline and diesel. The Jamnagar refinery, the world's most complex at 21.1, can process the heaviest, cheapest crudes and convert them into the highest value products. Complexity is competitive advantage. The more complex the refinery, the wider the range of crudes it can buy, and the higher the yield of premium products it can produce. A complex refinery can buy cheap, heavy, sour crude, trading at a significant discount to benchmark grades, and still produce gasoline and diesel that meet the most stringent specifications. Refining margins are thin, volatile, and deeply cyclical. Between 2000 and 2020, the average U.S. refinery margin, after operating costs, was approximately $5 to $8 per barrel. In 2020, during the pandemic demand collapse, margins turned sharply negative, and refineries around the world cut throughput or shut down entirely. In 2022, margins spiked to historic highs, $30, $40, even $50 per barrel in some regions, as post-pandemic demand surged and Russian crude and product exports were disrupted. This cycle, feast to famine and back again, is the fundamental rhythm of the refining industry. The refineries that survive are the ones that can process the widest range of crudes, operate with the highest reliability, and maintain the strongest balance sheet through the downturns. The ones that cannot, and every cycle claims a few, are sold, converted to terminals, or dismantled and shipped to a market where the economics still work. The episode 8 preview imagery, different crude grades in glass sample bottles, light golden to thick dark black, lined up on a table. Price charts showing the spreads between grades. A refinery operations center, screens displaying crude assay data, linear programming optimization runs, price feeds. A trader looking at a terminal displaying Brent versus Dubai spreads. The refinery has transformed the crude, but what was the crude worth in the first place? Not all barrels are equal. A barrel of light, sweet crude, like WTI or Bonny Light, produces a high yield of gasoline and diesel with minimal processing. A barrel of heavy, sour crude, like Mexican Maya or Venezuelan Mere, requires deep conversion and extensive hydrotreating, producing less gasoline and more fuel oil. The difference in value between the best and worst crudes can exceed $20 per barrel, $20 million on a single VLCC cargo. That is the subject of episode 8, the final episode of Crude, Grades, Benchmarks, and Beyond. What your barrel is really worth. Why Brent sets the global price. how WTI disconnected from Brent after the shale revolution, what makes Bonny Light Nigeria's most valuable export, how sulfur content and API gravity determine a crude's place in the market, and how traders arbitrage the spreads between grades, between regions, and between the physical and paper markets, the game that determines whether your barrel sells at a premium or a discount. This is CRUDE, a SeaMayors documentary series. Next, grades, benchmarks, and beyond, what your barrel is really worth. Helped you understand how crude oil moves from ancient plankton to the fuel in your tank, subscribe. And for the refinery engineers, the traders, the process technologists watching, what is the hardest unit to operate in your refinery? The FCC with its catalyst circulation, the coker with its drum switching, the reformer with its hydrogen balance. Drop it in the comments. The real knowledge lives in the people who run these plants.